Thank you for coming to my presentation. I'm Usik Lee, and I'm looking forward to introduce efficient multi-sensor aided inertial navigation with online calibration. Using multi-sensors has a lot of benefit compared to using just one or two sensors. It has more sources of information of both robot motion and the environment that allows you to perform robust and accurate long-term navigation. However, there are several drawbacks of using multi-sensors. One of the problems is that if you add more sensors to the system, then you have more sensors to calibrate. This increases the chance to have poor initial guesses about the calibration parameters and the system can fail. In order to survive from this problem, we need to adjust the parameters by online calibration. Another problem of using multi-sensor is that there are too many sensor measurements that often the estimator loses its ability to perform real-time estimation. The solution for this is finding a way to efficiently abstract the measurements to lower down the estimator's burden. In order to tackle these problems, we developed a multi-sensor aided inertial navigation system named MINS that can fuse IMU, camera, wheel encoder, GPS, and LiDAR measurements in a tightly coupled manner. The system can also do the online calibration of all onboard sensors, including the intrinsic and extrinsic parameters. Lastly, our system can run in real time, fully leveraging all the sensor measurements by efficiently compressing the information. We especially focused on abstracting the LiDAR measurements and was able to run the system with 20 Hz 64-channel LiDAR in real time by extracting the plane patches from the point cloud. The proposed system is developed based on our prior works. One of the core work is OpenBins, which is a VIO system integrating the camera and the IMU in MSCKF framework. This work is open sourced now. Another work is GPS VIO, which can fuse GPS information with VIO system, including initialization and online calibration. The latest component is VIVO, visual-inertial wheel odometry system, integrating the wheel encoder information with VIO, calibrating wheel intrinsic and extrinsic parameters online. The proposed system MINS combines all these works and also has the ability to integrate the LiDAR into the system. As the other sensor integration methods can be found in our previous works, in this presentation, I would like to focus on our efficient LiDAR integration method, which is a new feature of the system. There are several known hardships of using LiDAR measurements. One of the challenging problems is that it provides an overwhelming amount of sensor readings. For example, HDL64, the product of Velodyne, sends more than 2 million points per second to the system. Obviously, it is infeasible to process all these measurements in real time. Another problem is that the measured points do not represent the same physical locations. As each point gives information of different locations, it is hard to find the association between the LiDAR scans. Therefore, to fully leverage the LiDAR measurements in real time, we need to find a way to efficiently abstract the measurement and perform data association. To tackle this problem, we propose using plane patches that is extracted from the LiDAR point clouds. The small planes are the dominant structural information of the point cloud, so the information in the point cloud can be efficiently compressed in the form. Also, the plane patches are very convenient to find the association among them. Our method is composed of 4 different steps. First, we efficiently extract the plane patches from the LiDAR point cloud. Second, in order to further efficientize the system, we merge those patches that are representing the same plane. Third, we perform data association over multiple LiDAR scans in order to robustly update the state. Lastly, we update our system with minimal plane representation. The details of these techniques will be introduced in the following slides. First, plane patch extraction from the LiDAR point cloud. Given a new LiDAR point cloud, we sparsely select points from the point cloud. And then we utilize KD3, which is an efficient tool for organizing a space partitioning data structure to find the neighboring points of the selected points. Lastly, we compute the normal direction of the plane, assuming that the cluster of the points represent the same plane. Then we determine a plane patch using a centroid of the point cloud, the normal direction, and the corresponding uncertainty. I would like to note that all these steps are mostly linear, that computation can be very efficient. Also, the extracted plane patch will be treated as a point using the centered point and will be registered to the KD3 for later fast search and access. After plane patch extraction step, we are looking to find the patches representing the same plane and merge them. There are two reasons for this. First, those redundant patches representing the same plane will increase the computation. Second, it is clear that the more points used to extract the plane, the higher the accuracy can be. Therefore, it is better to have one plane patch composed of many points rather than two plane patches, each are composed of half of the points. Therefore, we perform this plane patch merging. Similar to the plane patch extraction step, we first sparsely select plane patches and find the neighboring patches using KD3. Then we test the same plane hypothesis between the selected patch and the neighboring patches to check if they're representing the same plane. The hypothesis is composed of two matrices, parallelism and point-to-plane distance. Once they pass the test, we consider they are representing the same plane and merge those patches. Merging can be done by re-extracting a plane from two patches points. In this way, we can reduce the computation and accurately represent one large plane with one plane patch. Now, let's move on to the data association step. In order to associate the plane patches over multiple LiDAR scans, we leverage MSCKF state that contains the historical poses of the IMU. First, we collect all the plane patches extracted from the LiDAR scans that can be bounded by the IMU poses. Second, we select one of the oldest plane patch and try to find the neighboring patches in the other LiDAR scans using KD3. We test the same plane hypothesis to check if they represent the same plane. Unlike the hypothesis of the merging step, this time the equation contains the relative pose transformation between the LiDAR poses, which requires the knowledge of the IMU poses. In this example, the IMU pose at 2 and 5 are required. However, due to the asynchronicity, it is possible that we do not have exact information at required time. In this case, we linearly interpolate the bounding poses and use the estimated IMU poses for the test. Once they pass the test, we mark them as associated. Finally, we update our state using those associated plane patches. However, we propose to convert the plane patch representation because it is overparameterized. The plane has 3 degrees of freedom, while our plane patch representation has 6, which can increase the computation and also can cause numerical instability. Therefore, we convert the representation to closest point, which is one of the minimal plane representation that is composed of normal direction of the plane and the scalar distance between the plane and the observer. The conversion between them are straightforward. With this minimally represented plane measurement, we now can update our state. The measurement can be modeled as a function of the current state and the old plane patch. As you can notice from the function, it contains the pose transformation between two LiDAR poses, which we may not have exact information in our state. We introduced that we solve this problem by interpolating the bounding IMU poses. To be more specific, the transformation can be represented by the bounding poses and the LiDAR spatiotemporal calibration parameters. As an example, you can find the role of extrinsic parameters in representing the orientation and how we model the LiDAR time offset from the bottom equation. We include all these calibration parameters in our state and calibrate them while updating other state. The full math can be found in our paper. To evaluate the timing and the calibration performance of the proposed method, we simulated the 20 Hz 64-channel LiDAR and use it to update. As the LiDAR sensing rate is 20 Hz, our goal is to achieve processing time less than 50 milliseconds. We recorded the timing on Intel i7 2.6 GHz processor in a single-threaded execution. The average performance during the simulation was as follows. The plane patch extraction took 12 milliseconds, merger 8, data association 1, update 25, and total 47 milliseconds, which was lower than the 50 milliseconds, showing its ability to process the overwhelming LiDAR measurements in real time. Of course, we don't want to achieve this real-time performance by just discarding the measurements. So we also look into the numbers of important items. The average number of plane patches extracted was around 1,500. Merger leaves more than 300 patches, found more than 1,700 associations among 9 LiDAR scans, and the average number of patches we used in every update was more than 100. This indicates that the system was fully leveraging the LiDAR information. Also, as stressed at the beginning of the presentation, the online calibration is important for a robust multi-sensor system. As shown in the figures, all our 6 runs of Monte Carlo test calibrating the LiDAR extrinsic and time offset quickly converged to the near true values and remained consistently. We also tested our whole system MINS on the real-world data to evaluate the navigation performance. The dataset is 11-kilometer long trajectory in urban environment and contains stereo camera, IMU, wheel encoder, GPS, and 16-channel LiDAR. We compared the MINS with different sensor combinated algorithms, VIO, GPS with VIO, wheel with VIO, and LiDAR with VIO. Our results shows that the LiDAR fusion with VIO was able to run 2 times faster than the real time, and MINS fusing all these sensors also could run in real time, showing the highest accuracy compared to other algorithms. I would like to summarize our work as follows. We developed MINS, which is an efficient multi-sensor aided inertial navigation system with online calibration. The system can manage heterogeneous sensor measurements efficiently, especially can abstract the LiDAR information and do association using plane patches. The system can perform the real-time estimation using IMU, camera, wheel encoder, GPS, and high-end LiDAR sensor. Thank you for listening, and if you have any questions, please let me know.